Before we begin, I'd like to give a quick shout out to our newest members, Xiangda, Xiangrong, and Ziyu, who just recently joined us. Now on to the main video. Hello everyone, my name is Dominic, and today I'll be bringing you through set theory. In your house, you usually have a bunch of similar objects that you group together. For example, you probably have a few forks, spoons, plates, and bowls that you put together in the same place. Forks and spoons go to the utensil drawer, while plates and bowls go into the dishes drawer, for example. Without directly knowing it, you have engaged with one of the most powerful tools in mathematics: sets. Sets can be loosely defined as a collection of objects that follow a certain rule. So in your homes, you already have a set of forks, spoons, and plates. But sets can describe more than just everyday objects. All throughout history, the intricacies of set has been studied and explored to the point where a new field emerges: set theory. Some well-known sets. Let's begin with something simple: numbers. You see them from a young age, interacted with them, stressed about them, or perhaps have fun with them too. But there is just one problem. It is very messy. Just like English, for example, lumping a bunch of words together without any rhyme or reason is really confusing and messy and rarely gets the point across. That's why we divide English language into different types of words such as noun, adjectives, verbs, among many others. Similarly, in math, we can divide number into different types: prime numbers, rational numbers, complex numbers, etc. Mathematicians divided number into several categories depending on the properties or function of those numbers, similar to how words behave in a language. And here is where sets can play a part. Since sets are essentially a collection of objects that follow the same rule, we can divide numbers into different sets according to their properties. For example, prime numbers are a set of numbers which are only divisible by 1 and itself. They are very special numbers that have been a key component in modern cryptography, something that helps keep your digital accounts safe. We usually write sets using curly brackets with elements or members of a set being inside those curly brackets. There are other sets of numbers out there that describe different things and they have different functions. Some numbers are used for counting, some numbers are used for accounting, and there are other numbers that describe shapes, numbers that describe electricity, rotation of three-dimensional objects, and so on. And since these sets are special, they get to have their own logo. Natural numbers are represented by N, integers by Z, rational numbers Q, real numbers R, and complex numbers C. These are not the only sets out there that have their own logo. There are many more sets that have their own logo, but these are the ones you would commonly encounter. What is important here, and what I want you to take home, is that a set is a collection of similar objects of some sorts. Numbers, just like any object you see every day, can be grouped together as a set, and whenever these symbols appear, it means a set of whatever particular number they have is being referenced to. Besides sets of numbers, there is one more set that is also special: the empty set. It is basically a set containing nothing, denoted with just a pair of curly brackets or a zero with a stroke. It is the smallest set possible with zero elements or members. This set has a lot of interesting applications. For example, mathematicians use the empty set to define numbers themselves. But in the interest of time, I will skip it for now. Okay, so far we've covered what sets are and what they can do, but there's more we can do when there are multiple sets. Set operators. When an element is a member of a particular set, we usually use this symbol, which looks somewhat like an E. For example, you can say that one particular plate is a member of a set of plates. When we want to say that an element is a member of two sets, we can use the intersection or AND notation, which looks like an inverted U or an N depending on how you look at it. This basically produces another set containing the elements that are part of one set and also part of another set. For example, if we have a set of spoons and another set of forks, the intersection would be a set containing sporks or spoon forks. Another notation is the union or OR notation, which looks like a U. This produces a set containing the elements of two or more sets. For example, if you have a set of spoons and we have another set of forks, the union between the two sets are a set of all utensils containing spoons and forks. Mathematically speaking, say we have a set A with members 3, 4, and 5, while another set B has members 4, 5, and 6. The intersection between sets A and B is another set with members 4 and 5. Meanwhile, the union between set A and set B would be another set containing 3, 4, 5, and 6 as its members. Notice that although both set A and B have 4 and 5 as members, when unioned, they appear only once. This is because in normal sets, order of elements and repetition doesn't matter. It's just that people like to notate everything in the simplest way possible. Another operator that is commonly used is the subset operator. This involves taking a set out of the set. Now imagine you have a collection of colored plates. Then, from that collection, you wanted to make a new collection of just the black plates. We call the new collection or set of black plates a proper subset of the original collection of plates, and we denote them with the symbol that looks like a C. If for whatever reason you wanted to make another collection of plates that contains all your old plates, we call this an improper subset of the original collection of plates, denoted with the symbol that looks like a C with an underscore below it. Subsets are useful for a whole array of stuff. For example, in your daily life, you've used the concept of subsets to organize files in your computer or organize the tasks based on some criteria. Subsets can be also used to subgroup guests in an invitation. Set builder notation. So far, we've talked about sets and what you can do with them. Now let's see how we can mathematically define sets. One way to define a set is by listing out all its elements, but in bigger sets, they're a hassle and can take a lot of time. Hence, to do this, we need a set builder notation, like this. Define a set S with members n, where n are all integers between 10 and 19 inclusive. Well, this isn't exactly how you would build a set, but it's almost there. We start with the set name, curly brackets, and then a variable, which is used to denote the elements or members of a set. That is followed by a vertical line and the rule that the elements of the set have to follow. Remember that earlier we've discussed that integers can be represented by the letter Z. This is where you can apply them. Since n is an integer, you can denote that n is a member of Z. We can also rewrite the second condition as 10 is less than or equal to n, which is less than or equal to 19. And finally, we can implement the intersection operator to join the two conditions to form our set. And with that, we are done. This is how you build a set using the set builder notation. With all of this in mind, let's connect all that we've learned so far into another related subject, probability. Probability is simply a chance of something happening, and we can measure this using sets, or rather the size of it. Imagine you have a set of utensils, spoons, forks, and knives. If you close your eyes, the probability of you choosing a spoon is basically the number of spoons you have divided by the total number of utensils you have, or basically the size of your desired set divided by the size of the universal set. The universal set basically means all the possible outcomes, in this case the total numbers of utensils. We usually denote the size of a set using the lowercase n. This is also where you can apply your knowledge of union and intersections. For example, the probability of you choosing a spoon or a fork is basically the number of spoons and forks you have over the total number of utensils. You can annotate it by using the union notation. While set theory may seem useless and obscure, without knowing it, we've all engaged with it in one way or another. We can see the application of set theory in real life from how you organize your stuff into different piles and how different piles of stuff interact with one another. You can also predict how likely something it is to happen, partially thanks to sets. That's all we have for today, and if you enjoy our content, don't forget to hit like and subscribe. Don't forget to check us out on Instagram, and we'll see you soon.